Assalamu alaikum. Bismillahir-Rahmanir-Rahim. I welcome you to the 30th lecture for the series of lectures on advanced computer architecture. Today, we will continue our discussion regarding the cache performance enhancement by using a technique where we reduce the miss rate. After a brief review of what we discussed last time, we will discuss the classification of cache misses and the methods to reduce the cache miss rate. Last time, we noticed that there are 4 basic options to improve the cache performance. These options are by reducing the miss penalty, by reducing the miss rate, by reducing the miss penalty or miss rate via parallelism, and by reducing the time to hit in the cache. Then we discussed 5 ways to reduce the miss penalty. We also noticed that the miss penalty grows as the processor memory gap extends. The techniques which we discussed last time include multi-level caches, the use of critical word first and early restart, and the priority to read misses over the write misses, and merging of write buffers, and the last technique was to introduce the victim caches. The first approach which we discussed, that is the multi-level caches, is basically the more the merrier, which means extra people are welcome to come along. This approach suggests that you may continue adding more and more levels of caches recursively based on the principle of locality until you achieve the desired lowest level of miss penalty. The second technique, critical word first and early restart, is the intolerance. That is, it suggests that you should not wait for the full block to arrive, rather start retrieving the word of the block that caused miss, and hence reduces the miss penalty. The third method, priority to read miss over the write miss, is the favoritism. That is, read is given priority over the write. This is against the normal sequence of the processor that waits for the read but continue after writing. The fourth technique which we discussed last time was merging the write buffer. That is acquaintance. That is combining sequential writes into a single block for fast memory transfer. The last technique, that is the victim caches, is salvage. That is, a small fast memory is added to the cache that recycles the discarded blocks when the unsettled primary cache wants a word that is recently discarded. All these methods help us reducing miss penalty. However, the first one, that is multi-level caches, are the most important and efficient. Now, reducing miss rate to improve the memory hierarchy performance is another important metric. Today, we will talk about the cache misses and methods to reduce the miss rate. Let us first of all discuss the classification of cache misses. Cache misses can be classified by 3 C's, that is, the first C for compulsory miss, second C for the capacity miss, and the third C for the conflict miss. The compulsory miss is also called the cold start or first reference miss. The first access to a block cannot be in the cache, so the block must be brought into the cache. So the compulsory miss exists even in an infinite sized cache of any type. The capacity miss is one where if a cache does not contain all the blocks needed during the program execution, then a capacity miss occurs. In addition to the compulsory misses, due to the blocks being discarded earlier but to be retrieved later, capacity misses occur in fully associative caches. The conflict misses, which are also known as the collision or interference misses, occur in case of set associative and direct map caches in addition to the compulsory and capacity misses. The conflict misses occur in case too many blocks may map to the same address or to the same set. Now, let us have a look at the two graphs showing the relative frequency of 3 types of misses for a fixed cache size and discuss how the miss rate changes with the block size. The first graph shown over here depicts the absolute miss rate representing actual data of the relative misses per thousand. Here, note that the miss rate for 8 kilobyte direct mapped or say one-way associative cache and 4 KB two-way associative cache is same, and the miss rate in this case is equal to 0.05. Similarly, the miss rate for 4 kilobyte direct map and 2 kilobyte two-way set associative cache is also same and is equal to 0.075. So this data here shows that the 2:1 cache rule holds for up to 128 kilobyte cache sizes. The 2:1 cache rule states that the miss rate of direct map cache of size n is about the same as a two-way set associative cache of size n by 2. Now, let us have a look at the graph for the percentage of relative miss rates in each category for the 3C misses. This graph shows that the compulsory miss rate is independent of the block size and is very small, whereas the capacity miss rate decreases as the block size increases, and the conflict miss rate decreases as the associativity increases. Considering how the miss rate for each of the three C's, that is, the compulsory, capacity, and conflict misses is affected, 5 different techniques have been introduced to reduce these miss rates for different types of C's. The techniques used to reduce the miss rate are using the large block size, using the large caches, introducing higher associativity, and wave prediction and pseudo-associativity, and last but not the least, compiler optimization. Now, let us discuss these techniques one by one. First of all, let us consider the larger block size. The simplest way to reduce the miss rate is to increase the block size. Larger the block size, it reduces even the compulsory misses, because by taking the advantages of special locality, larger blocks can have maximum number of the nearby data or instructions on the first miss. Thus, it reduces the chances of following misses which may occur if block size is small. However, where the cache is small, the larger blocks may increase the conflict and capacity misses. In order to study this further, let us have a look on the graph showing the miss rate versus the block size for 5 different sized caches. Here, each curve represents a cache of different size ranging from 1 kilobyte to 256 kilobyte. Here, note that when the block size is small, say 16 byte, data access is spread over multiple blocks, so the miss rate is high. However, the miss rate is also high when block size is much larger, but the cache size is small. For example, 1 kilobyte and 4 kilobyte caches with 256 byte blocks have higher miss rate as compared to the 32 byte blocks. The example graph shows that the larger cache of 64 KB or 256 KB should be used for 256 byte blocks. However, the larger block size may also increase the conflict misses and even the capacity misses if the cache is small. Also, the larger block size increases the miss penalty as it increases the memory read and write cycles and hence the average memory access time. Thus, a cache designer must make a compromise between the cache size and the block size to reduce the miss rate such that the miss penalty does not go too high, as increase in the miss penalty may outweigh the decrease in the miss rate. Here, in this example, let us find the block size that has smallest average memory access time for the miss rate of the caches shown in the graph. Here we assume a memory takes 80 clock cycles of overhead and then it delivers 16 bytes every 2 clock cycles. That is, it supplies 16 bytes in 82 and 32 bytes in 84 clock cycles. Here, assume that the hit time is 1 clock cycle. Then let us find the average memory access time. Here we know that the average memory access time is equal to the sum of hit time and the product of miss rate and miss penalty, which can be expressed as shown over here: hit time plus miss rate multiplied by miss penalty. Using this expression, let us find the average memory access time. Here, the graph shows that for the 16-byte block in 4K cache, the miss rate is 7.24%. And as given in the early data, with the example, the miss penalty is equal to 80 plus 4, which is equal to 84 clock cycle. Therefore, using these values, we can find out the average memory access time as it is equal to 1 plus the product of 7.25% and 84, which results in a value of 7.082 clock cycles. Similarly, the miss penalty and average memory access time for caches of size from 4K to 256 KB using the data obtained from the miss rate versus the block size graph shown earlier is calculated, and the calculated values are shown here in this table. The results shown in the table show that for a substantial increase in the block size, that is 16 byte to 256 byte, there is a small increase in the miss penalty, that is from 82 cycles to 112 cycles. The values given in the table also show that the miss rate and hence the average memory access time is not smallest for largest block size. For example, for 4K cache, the 32-byte block gives the minimum average memory access time, and 64-byte block size is optimum for 16K, 64K, and 256K caches. Now, concluding our observations regarding the use of larger block size, we can say that the selection of block size depends on both the latency and bandwidth of the lower level memory. Moreover, high latency and high bandwidth encourages large block size since the cache gets many more bytes for a small increase in the miss penalty. So, with this much discussion about the use of the larger block size, let us discuss the second technique, which suggests the use of larger cache size. The approach to reduce the miss rate using larger cache size is useful to reduce the capacity misses. However, it is popular only for off-chip design. As it was in 2001, the size of the second level and third level caches was made so high that it approaches the size of the main memory. However, this technique has a drawback that it has longer hit time and high cost, that is high access time. So due to these drawbacks, usually this method is not preferred over the other methods which we have to discuss now. The third method to reduce the misses is to use higher associativity in n-way associative caches. Now, in order to understand this approach, let us once again have a look onto the graph which we considered earlier, showing the miss rates versus the cache size. This graph shows that the miss rate improves with the higher associativity. However, these curves show two general rules of thumb. The first one is that for all practical purposes, 8-way set associative is as effective as the fully associative in reducing the misses for caches sized up to 128 KB. And for caches sized 32 KB and more, the overall miss rate does not depend on the associativity. The second rule of thumb is that the direct map cache of size n has about the same miss rate as a two-way set associative cache of size n2. This rule holds for caches less than or equal to 128 KB. Now, let us discuss that where higher associativity reduces the miss rate, what is the impact on the other aspects. The practical data shows that the higher associativity comes at the cost of increased hit rate, and it could increase clock cycle times. The clock cycle time for two-way up to 8-way associative caches can be related with the one-way associative cache as shown over here, that the clock cycle time for two-way set associative is 1.36 times clock cycle time for one-way associative, and that for four-way associative is 1.44 times the clock cycle time for one-way associative, and similarly for 8-way associative cache, it is 1.56 times the clock cycle time for one-way associative. Now, let us assume the hit time of one clock cycle and miss penalty of 25 cycles, and use the miss rate for different sized caches from the previous example. The average memory access time for one-way 2-way, 4-way, and 8-way associative caches is calculated and shown over here in this table. Here, note that the average memory access time reduces for the caches less than or equal to 8 kilobyte for up to 4-way associative caches. It is shown over here as the white area. And starting with 16 KB caches, the greater hit time, which is 1.36 up to 1.52 times for one way, it outweighs the time saved due to the reduction in miss rate, and it results in increase in the average memory access time. Now, with this much discussion about the use of higher associativity, let us take up the fourth approach to reduce the miss rate. The fourth technique, that is the way prediction and pseudo-associativity. This technique combines the fast hit time of direct map caches with the lower conflict misses of the set associative caches. Thus, it reduces the conflict misses while maintaining the fast hit time of direct map caches. In order to understand the basic concepts of way prediction and pseudo-associativity, let us first of all define what do we mean by the way prediction. The way prediction means that predict which block in a set is likely to be accessed by the next memory access hitting this set. Now, to accomplish the way prediction, we usually take the following steps. Number one, extra bits are kept in caches to predict the way or block within the set of the next cache access. For example, in a two-way prediction, single bit is used to select which of the two blocks to try on the next cache access. And in a four-way prediction, 2 bits are used, and so on for 8-way and 16-way caches. The second step is the multiplexer is set early to select the desired block, or only single tag comparison with this block is used. This is a cheaper approach opposed to the comparison with all the blocks of the set, which is usually done in set associative caches. The simplest prediction remembers the last word accessed, and a miss results in checking the other blocks for matches in subsequent clock cycles. That is, higher cost is involved to check non-predictive blocks. This means that the block which has been predicted, it requires lesser time, and the block which has not been predicted, it requires more time. This technique has been used in the alpha 21264 system, which results in the latency of 1 clock cycle if prediction is correct, and the latency of 3 clock cycles if the prediction is incorrect. Now, let us see what do we mean by pseudo-associative or column-associative caches. Here, in case there is a hit, the access proceeds as in direct map caches, that is, it compares the tag on the block. Whereas on a miss, before going to the next lower level memory, a second cache entry is checked at another block in the pseudo set. The simplest way to check another location in the pseudo set is to invert the significant bit of the index field to find another block. This actually means that for two-way associative, the index field value is inverted to find out the first set or the second set. The pseudo-associative caches have one fast hit time and one slow hit time, corresponding to the regular hit and pseudo hit time. The performance of a pseudo-associative cache is measured by counting the slower hits. If most hits become slow hits, the performance degrades, whereas it remains good otherwise. Now, with this much discussion onto the way associative and pseudo-associativity, let us consider the last technique to reduce the misses. The last technique is known as the compiler optimization. Our earlier discussion so far regarding the use of first four methods to reduce the cache misses, they suggest some methods to modify the hardware or to include some additional hardware in the caches. The compiler optimization approach reduces the cache miss through software. This method helps to reduce both the data cache misses and the instruction cache misses for a fixed cache organization. Let us discuss how a compiler optimizes instruction code and the data for the reduction of misses. So first of all, let us talk about the instruction or code optimization. The method used for the instruction or code optimization is known as reordering the procedure in the memory such that the conflict misses are reduced. And the second way is using cache line alignment of basic blocks. Here, the code reordering ensures that the procedures used frequently do not map to the same blocks or same sets, and it determines the conflicts by profilings. That is, it prepares a profile, and from the profile, it determines the conflicts. Whereas the code line alignment method decreases the likelihood of cache miss on sequential code by aligning basic blocks so that the entry point is at the beginning of the cache block, whereas the data misses are reduced by reordering data patterns to improve the spatial locality and temporal locality of data. For example, array calculation can be changed to operate on all the data in a cache block rather than blindly striding through arrays in the order the programmer places the loop. Now, in order to explain this thing, let us consider two examples. First, the use of loop interchange, and second, blocking technique. With the help of these examples, we will try to understand the code optimization that reorders data access patterns to reduce conflict misses. Here, let us first of all consider an example for improving spatial locality. For this, let us consider a program having nested loops that access data in non-sequential order, say for j ranging from 0 to 100, and in sequential order for I ranging from 0 to 5,000. Now here is the first version of the program where we are having three nested loops. The first loop is for value of k, which is having iterations equal to 100, whereas the second loop is having 100 iterations, and the third loop has 5,000 iterations. Here, the code skips through memory in steps of 100, that is for column j, and it requires that all the 5,000 values for row, that is I, be available in the cache using spatial locality principle. This shows that in order to execute this program and based on the spatial locality, all the 5,000 values must be available in the cache. However, we can enhance the performance and reduce the size of the cache by reordering the code. Let us have a look on the reordered version of this code. Here, in this reordered version, the second statement is swapped with the third statement for the first order program. The reordered program, therefore, looks like this, where the first loop is for k ranging from 0 to 100. The second loop is for I ranging from 0 to 5,000. And the innermost loop is for j, which is from 0 to 100. So this reordered version of the program accesses memory sequentially for all 100 values of j for each of the 5,000 values of I. Thus, it improves the special locality as it requires only 100 values in the blocks to be fetched in cache instead of 5,000 values as in the earlier case. The second compiler optimization technique uses blocking. The blocking technique is suitable to improve the temporal locality. Let us consider an example of a program and see how we can use the concept of blocking to improve the performance of a cache or to reduce the misses in the cache. For this, let us consider a program which performs matrix multiplication. Here, we know that for the matrix multiplication, we have to deal with multiple arrays with some of the arrays accessing data row-wise and some accessing column-wise. Thus, storing arrays as row major order, that is row by row, or column major order, that is column by column, it will not help the temporal locality for such a problem, because in this case both the rows and the columns are used in every iteration for matrix multiplication. This we can observe with the help of an example program shown in the C language over here. Now, in this first initial version of the matrix multiplication code, there are 3 loops which are being used. The first for loop is corresponding to the I, which is ranging from 0 to n. The second is for j, ranging from 0 to n. And the last one is for k, which is also ranging from 0 to n. Here, in this case, we assume that the matrix Y is multiplied with the matrix Z, and the result is placed in matrix X. Now, note that the innermost loop corresponding to K, it reads all the n by n elements of the matrix Z. And the second inner loop corresponding to J, it reads the same n elements in a row of Y, and it writes one row of n elements in X. Now we know that the capacity misses depend on n, that is the number of elements in a row or the number of elements in a column, and it also depends on the size of the cache. If the cache can hold all the 3 n by n matrices, then there will be no problem, as there cannot be any capacity miss. However, if the cache size is small and it can hold only one n by n matrix and only one row of n elements, then the full matrix Z and one ith row of matrix Y can stay in the cache. Else, the misses may occur for both X and Z arrays. Note that In this example code, the 3 loops perform n cube operations on all the arrays, where the innermost loop, that is for k, it accesses x for n squared times. It accesses y and z arrays each for n cube times. Hence, there would be 2 multiplied by n cube plus n square memory word accesses for all the n cube operations, and in the worst case there would be 2 n cube plus n square misses. Note that the misses occur as all the 3 arrays cannot fit into the cache. Thus, to ensure that all elements being accessed can fit into the cache, the original cache can be changed to compute a block of the matrix of size b by b, where b is referred to as the blocking factor. So here we mean to say that instead of executing the matrix multiplication operation for the full array at a time, we take up only a block of size b by b and we perform multiplication onto the block, and then we perform this operation repeatedly on all blocks of the array. Here, B is chosen such that one row of B and one B by B matrix can fit into the cache. This ensures that the array Y and Z blocks are resident in the cache. Now, the revised code for the blocking is shown over here. Now, this modified code shows that the 2 inner loops compute in steps of size b, that is the blocking factor, rather than the full n by n size of arrays x and z. Here, note that the total number of memory word accesses is 2n cube divided by b plus n square. That is, there is a total improvement in the capacity misses by a factor of b. Now, with this much discussion onto the blocking technique, which is useful for both improving the spatial locality and temporal locality, we have presented basically 5 different methods to reduce the miss rate. Today, we first presented the 3 C's model of cache misses, which led us to the 3 optimizations. That is, the large block size that reduces the compulsory misses, large cache size that reduces the capacity misses, and higher associativity that reduces the conflict misses. The way prediction techniques check a section of cache for hit, and then on miss, it checks the rest of the cache. The final technique which we discussed today, that is the loop interchange and blocking, is a software approach to optimize the cache performance. However, today we will stop over here with this much discussion about how to reduce the miss rate. Next time, we will talk about the way to enhance performance by having processor and memory operating in parallel. Till then, Allah Hafiz.